Let me start with, I summarize a little bit what I said, content of my previous lecture, and then we continue. And so, actually, was it that I start with some such kind of matrix, and this matrix understood as permutation relation, or people are calling these diagonal R matrices, or many other ways. But anyway, with this we can construct the quantum group, and I did not explain the whole definition of this quantum group, but at least I had definition of UA of n, which is some algebra generated by Yi. It is nilpotent Ym, where this is matrix M times M. Yes, and just this is as algebra. This is algebra with generators Ym, and it equipped with co-multiplication, the U to U times U, and but this tensor product we understand slightly non-usual way, where we use this, but this is co-multiplication. It means that this map is has co-associative property. And by the way, as usual in the quantum group business, if you have this, you expect to take U star and get the structure of algebra there. And we have it just from this. And dual algebra up to some slight modification is just isomorphic to U. And this is, again, main things. Then, what was it? Suppose we take it. Next things is that we can construct the, not a representation, but maybe what is reasonable to call maybe Bosonization or something like this of such kind of algebra. Bosonization is the map from this to algebra of skew polynomials. And if we construct such map, how we did? That in this case, we have very simple representation of this algebra to polynomial in one generators, which now I can denote by any letter, say x, for example. And this is pi I, and it means that in such map, all generators are going to 0 with respect to yi, and this yi is going to x. And if we have this, then elements from 1 to m, yesterday m was 2, but I call colors. If we have any sequence of colors, and colors can repeat surely, then alpha 1, alpha 2, alpha 3, and so on, some s, then I can consider the tensor product of this. So it means that tensor product of this gives me a map from universal enveloping first to tensor product of S copies of tensor enveloping, and it send us to C x1 alpha 1, x2 alpha 2, and so on, x s alpha s. Sometimes I like inverse, but right now I just do not write it. And we have such a map from U to this. And in principle, this sequence of colors can be arbitrary. Yes, and no, about such kind of map, no, as I said, that such in almost all cases, no, the structure of this algebra depending in A. So if A is generic, then no Hopf ideals, and so this algebra is just free algebra. So it means that this map has very big kernel. Yes, and also if A is special, for example, it is corresponding to matrix Q square, Q square, Q minus 1, Q minus 1. In this case, corresponding nilpotent algebra is nilpotent algebra for quantum SL3s. So, and it has two generators, Y1, Y2, and this algebra, and size of this as polynomials in 3 generators, and the third generator is Q bracket of Y1 and Y2. And actually it is, in this case, this algebra is small, and we can take a map from example like this: x1 color 1, x2 color 2, and x3 color 1 again. And we can take map from U to this. And in this case, it will be embedding to polynomial ring in 3 variables. Yes, and if we take more colors, not colors, more maps, then x4, 2, x5, 1, and so on, then it is like this. But let us look what I explained yesterday, and it is good to repeat it because it is important that we can know our construction, which is actually imitate the situation in representation of Virasoro, of field theory, and so on. We had infinite letters and infinite, and I consider the coloring 1, 2, 1, 2, 1, 2, and so on. And still, let us have in mind this case. So in this case, well, it looks the same, but now just this may be infinite if we like. Then nilpotent algebra, universal nilpotent algebra, is mapping into these polynomials, skew polynomials in infinite number of x alpha. And the generator y1 is going to what we call screening, the sum of all x's which colored y1, and y2 the sum of all which, yes. And definition of W algebra was what commute with such kind of screenings, but what actually I explained yesterday, let me say just the same, but probably in a little bit, using a little bit different words. So how to understand what is going on? So this, suppose it is position, say this is position 0, this is position 1, 2, minus 1, minus 2, and so on. Then what I did, I could take something which expressed through this. In principle, we can take x0, 1, and even formally write down this, and x1 color 2, and it will be, say, lambda 1, it can be lambda 2. Yes. And after that, I want to say that in whole this story or on this algebra, we have the adjoint action of the corresponding quantum group. Adjoint action is usually given by brackets, and here is the same. So I take S1 and S2, which are sum of y's, and adjoint action of each of them is Q bracket. Add S1 or add S2. Yes. And so what they produce, we can understand it by the following way. I want to draw a line. Suppose we have such kind of product, x0. No, such product we put here. And then I start to calculate these brackets. And these brackets give me what? As I explained, one bracket gives me this times some sum of, say, x1 here, or on this infinite segment, on this half of a line. Yes, and if I do it twice, then it gives us something like double sum. And it is good to understand such kind of thing. It is not very rigorous now, but as a point which is easy to understand, it is following. What we have here, actually, it is something living here, let us denote it by O, times something which is living here, which can be understood is in some kind of integral from minus infinity to this point, 0 in this case, and here I have S1 T1, S2 T2, S1 T3 maybe again, T1, T2, T3, and so anyway what we have here will be the linear combination of such kind of things. Yes, and what is happening in reality, if we are doing it here, it's very close to such picture. And then after that, we can understand what is going on by the following. That we have, for example, such product, or maybe we can take similar story this, but times some x's maybe in integer powers, but this x is not far from this place. And so, again, naive description is following. We have some local data, local object, times non-local things. It is a collection of tails. No, collection is tail is some multiple integrals which we have here. And then I also said these tails are what? Tails are tails are living somewhere here, and tail is the sum of xi of color 1, and second the color of xi of color 2. And as I explained, that algebra which generated by them is isomorphic to this. Therefore, at least it is also almost correct that the space and so, or algebra even, if where we're working is what? Is local part times universal enveloping of n, which is corresponding to these tail things. First of all, here on this part, we have the action of Si, which are acting by a joint way. Yes, and other part, which I explained, is following. That we can take un, and we have co-multiplication from un to un times un. Yes, and if we take any element beta belong to ui n star, then such element gives us a map. No, how? I want to have that we have some operator, maybe bad notation, but beta, such beta, I want to apply to this A. Now beta from here, A belongs to A n. So how I do it? I take A and this delta A sends this to such product, and then I pair it with one I pair it with beta here in this second. So beta give me a map from this to maybe better explain it by this way. Yes, and beta sent this map to take x times y here, and it sent it to x times y beta. Yes, and so as a composition, beta gives me a map from this to this. And so by this way, dual space, this U star, gives me maps to operators acting here in all things also. But if you look carefully what is going on, actually U star, as I said, is an algebra, and this algebra is acting here in this part. Therefore, on the whole story, we have the action of two things. First, U is acting by adjoint, as I said, and U star, which actually I explained the action of generators, but whole things are acting by this way, acting here. And U star actually generate some algebra, and such kind of construction is one of the possible way to determine a double. So, no, double is usually determined by but Drinfeld did it. Actually, I think he did it more or less by this way, but the usual definition is some kind of formulas. But this kind of construction means that we have some space where U is acting by one way and U star is acting by other way, but then because of some reason, mysterious or not, altogether they give us the action of some big algebra. And it means that actually here, more precisely, it means that here we have action of U and U star. And because it is, all object is graded, so it means that Cartan, which determines this grading, is also acting here. And up to slightly changing of generator, as I said, this U and U star corresponding the action of Drinfeld double of U or corresponding quantum group. So, so what is going now? That we have some kind of algebra, and no, first, no, to discuss what does this action mean, I think it has some meaning and it is necessary. But what we have actually, we have some algebra. And this algebra is, in this description, is local things, local objects with tails, or more precisely, it is like this, and U stars are acting there, and altogether it gives us the action of a quantum group which corresponding to this matrix A. And now what we are doing when we no, our initial problem was following, that we had xi, and maybe also with colors, and also xi with colors inverse. Yes, infinite or not does not matter, but we considered zero part of this 0 degree, where it was expression like x alpha. 0 degree in this alpha. So I can take x alpha and x alpha plus 2, it has same color inverse. So a color gives us grading, and I wanted to consider from this point colorless things. And then our double algebra is something what commute with S1 and S2. And so what does it mean from this maybe a little bit more sophisticated version of what is going on? First of all, on the whole algebra, acting the graded Cartan, such that Cartan on zero grading acting by 1 or 0, depending how we determine this Cartan. So it means that the zero component, zero weight component of my algebra is something which is stable with respect to Cartan. Then in the definition of W-algebra is I am interested in element of degree 0, A, such that Si with this is 0. On this language, it means that adjoint action of Si to such part is just 0. And third things, that I interested in local things. Local things which they do not have tails. Because in my construction, annihilation operators, I kill tails. So it means that local things, it is such that are stable with respect to action of U star. Therefore, the conclusion of this is following, that we have some algebra A where quantum group is acting, and W-algebra just invariance with respect to this invariant subalgebras with respect to this action. Yes, and no, and how in principle it can occur? So invariant, non-trivial invariant part can be found in a case when quantum group is relatively small, and if it is corresponding to finite dimensional algebra. For example, if Cartan matrix is this, that the corresponding quantum group is UQSL3. Yes, and then in this case, you can expect something what is going on? That the space where we're looking for invariant, it is something like this, and here it will be some number of x's. x1, x2, x3, x4, x5, and maybe many of them. In principle, infinitely many, but even finite number is also interesting, and colors 1, 2, 1, 2, 1, and so on. Yes, and then we have what? In this case, this things is something which has a size of polynomials in 3 variables. In this case, it is 5. And then I have the action of quantum group, which, no, in this case, SL3, it has dimension 8. So, but we can expect or not the invariant even here. But if we have more of them, then invariant part gives me some algebra. And this algebra is W-algebra in this approach. Yes, and No, in the case when no, the question which I tried to explain later, but maybe not immediately now, because maybe end of today's lecture or next lecture is following. Then what is going on? Suppose, for example, that A is more complicated. So it can be affine, or it can be generic, and so on. Now, in this case, corresponding quantum group is big. But still we have something like this. Suppose here we have some finite number of x's. And so we have some algebra where corresponding quantum group is acting. And the question is, what is this? Now, first of all, this question has a meaning in a case when we have not x's at all. So what is going on here in this case? Here, UAN, it is just algebra, and here we have generators AI, and they are just generators from this, and they are acting on this space by a joint way, and U star is acting as I explained. And what kind of picture we good to have in mind here? But it is what? It is, in this case, it means that we have universal enveloping of some quantum group, and this quantum group is acting on the corresponding flag manifold. And on this flag manifold, we have open set, maybe we have a Schubert decomposition, and W is the open set, and it is acting there. And by this way, just space of function on this open set. And such kind of representation, or such kind, it is the most natural way to have some algebra where quantum group is acting. But if we have this times some amount of x's, then it is still object where, again, if the corresponding algebra is not finite dimensional, even affine or something like that, then, and suppose this number of x's is finite, then we have something which is slightly bigger than this flag manifold, but the group is acting. So how it is acting, it is not very easy to describe, but on these actions, it is almost transitive. So it is quotient of the corresponding group by some subgroup. Yes, and this subgroup is surely depending on such axes. And yes, and so this is the object which we have to study in this case. And in affine case, if we have infinitely many x's here, then it is possible to describe what is this. And it will help in understanding what is going on. So basically, such kind of construction I explained yesterday, and integral of motions, critical level, and things like that. I will try to say something about this a little bit later. And now let us go to Virasoro business and W-algebra business, and so on. I want to first to explain what is going on here, and then try to connect it with this latest picture. But Virasoro, or probably the situation in general. So what is our question so let us fix some vector space H, and this H will be space with quadratic form, which will be a non-symmetric quadratic form, which will be not degenerate, and all spaces are determined over complex number. Yes, and this will be Heisenberg algebra. Yes, and my notation, which I have to introduce, will be the following. No, Heisenberg algebra is surely H times something like this, T inverse, or sometimes I have in mind Laurent polynomials, plus central. And central extension I given by Fg is K times residue pairing df and G, so the same formula which I used in one-dimensional case. Yes, and this is algebra H times 1 is according to this, because this is differential is center. It commutes with all other elements. Yes, if P belongs to this, then this is Fock representation, and it means that it is highest vector Vp that such that H times 1 H times Ti, first of all, is 0 if I is positive, and H, element H times 1 applying to Vp, H belong to this is P H times Vp. Yes, and now screenings. Screenings, no, we usually formulate problem by the following. For screenings, I need no, if I take some Q, Q is bad letter, maybe some L from H, then first I determine some representation RL, and this is a representation with the basis Fi, such that the action, just like in one-dimensional case, if I take H times Ti, I apply to Fg, it is fi plus g, and coefficient here is h. It is like this. Yes. So L we always identify with H. We identify with H star because we have form there, and we can forget about star. Yes, but now the problem about W-algebra. Then again, I need to, I explained, I will not have possibility to repeat it again. Suppose I fix vectors L1 and so on Lm. And I have sequence of representation R L1 and so on R Lm. Then follow the ideas and construction which I explained yesterday. I can construct bimodals R L1 bar and R Lm bar, and in each of them R is subspace. And so I have element F0 first, F0 second, F0 M. It is zero Fourier component from the corresponding R. And they are calling, this sum of these elements are calling screenings, and W-algebra in standard definition is what commute with them. Yes, and we can describe this by the following way. Let us take some representation. No, in principle, it is not very important which one, but I take some representation of Heisenberg, say F0. Then suppose I fix number of vectors, L1, L2, and so on, and Ls. Yes. Then each vertex operators, as I explained, this is symbolically it was like this. I have L1 here, for example, and L1 is here. It is subspace here, and we have F0 to F L2. We have R L2 here, and so on. Yes, and it is a vertex operator. It's just embedding of this simple representation of my commutative, actually, Heisenberg algebra inside the homomorphism from this to this. Then I take from here, here, and here elements of 0, the choice, in principle, the choice of 0 Fourier component is not very important. We can choose any elements. And the formulation of the problem, in principle, can be the following. I have such collection of RLI, which are vertex operator from this to this. In each RLI, I have some element BI. This is element from here. And I can fix them. And after that, I can ask what kind of algebra commute with this, and so on. So this is definition of W-algebra, but let me consider some example. This example I like very much, and it is special case of this. And this is example which I want to call fermionic screenings. And no, this example is, first of all, interesting and not so old as a story what I explained before. But let me explain a little bit how it is going. So first, let me take psi I and psi I stars. It will be fermions. It is a Heisenberg algebra, so it means it's psi I, psi j plus is 0, same with stars, and only non-trivial brackets, psi I and psi minus I star plus is 1. And we can no, first of all, they are vertex operator. And it's a special case of what we are talking about this. So what is this? This is calling by one-dimensional lattice and with length 1. And so how to do it? If I write hi, the sum of psi alpha, psi beta star, alpha plus beta equal I, then such hi is Heisenberg. And the situation is following, that we have, this is Heisenberg, and if I take these fermions and consider the standard representation of these fermions such that vector v is killing by psi I if I is positive and psi r star v is 0 if, then the corresponding space is looking like this. It is highest weight vector, then psi 0 is acting here, and it is looking like this. It is psi 0, it is psi minus 1, it is psi 1, and so on. And here they are representation of this Heisenberg. Yes, and even in this case, we can start to play to this game. And it means that we can ask, no, again, Heisenberg is Heisenberg, it is hi. Here we have representation of this Heisenberg. In my notation, it is f0, it is f1, it is f2, it is f minus 1, and so on. and operators are acting from this to this, and I can take psi 0 as screening operator. And in principle, I can take psi 0, or I can take any combination of them as a screening operators, and then I can ask which operators are commute with this psi 0, what part of our Heisenberg is commute with 0, but in this case, it is not big deal because we can take, no, because it is fermion, it is very easy to construct something which commute with it. And we can take for example, such kind of expression, this is derivative, commute with these things. And skew commute. They commute because the only things which does not commute with psi 0, it is psi 0 star. Therefore, we need the expression which does not contain this. And if we want only expression which are acting, which has degree 0, then I can write down something like this. Psi I, psi j star times j. I plus j equal alpha. And this is expression which is surely commute with this, because it is this. And we can determine this as L alpha. And this L alpha, if you are looking what is this, they give us Virasoro algebra. And this Virasoro algebra has central charge C equal -2. Yes, and this is a special case of construction which we are talking about. But in this case, we have many other operators which are also good. I can put G square here, for example, or something, any polynomial, so only I want that psi G, psi 0 star does not appear, then it is elements from my W-algebras. You can ask for example, the following thing, that in principle, we even can do the following. No, it is just interesting to mention what kind of example we can do if we can take it seriously. So, for example, we can do the following, that even in this case, in principle, I can take psi 0 and psi 0 star and ask what algebra is commute with both of them. Or I can ask the following things. I can take, well, in my space, operator psi alpha and operator psi alpha star are acting, and the space with the basis psi alpha belongs to Z, gives me the, it is Laurent polynomials, but in principle, I can consider like this, because this is Laurent series, because to each vector psi alpha, if alpha is big enough, is acting by 0. So they are Laurent polynomials, and I can take, for example, two-dimensional subspace here. And it will be a two linear combination, suppose even infinite, but we do not afraid the infinite sum here. And we can ask what part of our algebra commute with both of them. This is also a special case of our story. And no, maybe I do not want to explain details here, but it is just good to say what will be result in this case. Result is following. We can take, we can consider absolutely different situation or from the first glance. So we have UK as L2 hat. No, this is universal enveloping of current algebra, and K is level. And as I mentioned several times, that K equal -2 has the special interest, because in this case, corresponding universal enveloping algebra, it has big center. No, maybe it is not reasonable to explain why this center is big, and but we have big center here, and this center has its own spectrum, so it is functions on something. And these somethings, in this case, can be identified with a differential operator of second order, which is usually calling opers for SL2. Q here is belong to C Z inverse. Yes, and because we have such kind of data, so what we can do? If I have big center acting, and if I fix such element, then it determines me the again, as I said, the element of spectrum of the center, or it defines the center character. Therefore, I can form a new algebra, which is -2, because it is this, and suppose it is chi. Let me put chi here. I factorize by central character and get something smaller. Yes, and it is this, but I also need some smaller algebra. Actually, it is no, I skip some details, but situation is following, that I can take this. Here I have also some Heisenberg, and actually I need to make some kind of reduction of the Heisenberg. How to do it, maybe I do not want to explain, but what I want to say is following, that here we have some collection of algebras which are labeled by these authors. And here we have the collection of algebras which are labeled by two-dimensional subspace in the space of Laurent polynomial, of Laurent series. And if you take two-dimensional solution, two-dimensional space, that it is not always, but we can, if we have this, we can find the differential operator of second order such that this C2 are zero mod of it. And what I want to say that the algebra which we can construct by this way and the algebra which appear by this way, they are very, very, very much close to each other. And actually, this algebra is what we have to do. I have fixed chi, and then, but Heisenberg is still acting here. I have to consider cassette with respect to this Heisenberg. Consider highest weight vector with respect of this Heisenberg. I get some algebra. It will not be vertex operator algebra because we have not Virasoro here. But this is also not vertex operator algebra from this point. But if you relax definition, it is something similar to vertex operator algebra, and I want to say that such kind of things are really coincide. So we can construct the situation on a critical level using this screening construction, which is also interesting and give us some hopes. Well, and even in this example, it is good because I wanted to explain how, now suppose, let us return to to the case not so complicated. I mean that if I want to describe vertex operator algebra which just commute with psi 0. Yes, and let me use my yesterday language. So here I'm just talking algebra, but yesterday I said that it is some language of currents or correspondence between elements of vacuum representation and elements of algebras. And what was it? That in this example, I have just Heisenberg, but now I understand this as a vertex operator algebra. And vacuum representation of this vertex operator algebra in notation which I had is F0. So it is vacuum vector, then I have H minus 1, is just H minus 1, then I have H minus 1 square H minus 2, and so on. Yes, and as I said, using yesterday co-invariant language to this h minus 1, I correspond current hz. To this h minus 2, I correspond and actually h prime z. And so this is just hi z minus I, and here the formal derivative in z or z over dz, it depends how you understand it. And so there are such kind of operators. And I recall that h minus 1 square, I correspond the h z squared two dots, and which is more complicated operators, sum of h alpha, h beta, alpha plus beta equal I. It is expansion of this. Then I want to know what kind of corresponding operators commute with this psi 0. And they're not representation theory, but probably this picture says us what is this. No, first of all, no, it is our Fock spaces, but first, if I want a correct formulation, I need to shift this numeration. 0 here, 1 here, minus 1 here, and it is like that. No, I did not explain actually. No, it depends how I numerate them. Yes, anyway, now I want to formulate the statement. So, so again, what is happening here? I have this collection of Fock spaces. Between them, I have the action of operators, so phi 0 acting from this to this, from this to this, and other components are also acting. Yes, and if I want to formulate what I want, first I need to extract this part. It is F0, and it is F1, and operators psi 0 acting by this way. Yes, and for example, component psi minus 1 acting by this way, and psi 0 from here to here now acting by this way. Yes, anyway, this psi 0 gives me operators acting from this to this, from this to this, and so on. Now I want to formulate the main statement about this, that let us take a vector from this F0 W such that psi 0 from this vector is equals 0. Yes, and then I can take this vector W and produce the current from it, and the statement is that this current commute with this screening. No, I think the at least formulation is clear. The mystery may be why I choose just this segment, and no, actually this is a consequence of rather simple calculation, which maybe it is not good to present now, but at least what? So this is some operator which is acting from this to this. And for example, it is from the first level, it is acting to this. And this vector is not in the kernel, yes, and actually operator psi 0 is acting from this to this. And here is two-dimensional space, and here is one-dimensional space. And we have one vector here which belongs to a kernel of this. And I have taken him, in principle, to some linear combination of them, and construct operator from it. And this operator will be just Virasora, what I explained you before, and it was written somewhere. It is just this. Yes, and so it is written in terms of psi star and psi, but actually it is not completely evident, but it is possible to write in terms of h's, and so it is like, it will be like this. Yes, and no, to understand it, you need to write a problem. It is better not to do it on the blackboard, just how these correspondence vertex vectors and operators are working. No, it is easy things, but explanation on the blackboard, I do not think add you much. Yes. But the result of such things are following, that no, it is a sort of prescription actually, but suppose you want to know which elements like this commute with screenings, and no, generalization can be what? That we have Fock space, yes, F0, and no, here this is vertex operator, and here this number is 1. But suppose this number is not 1, this is not 1, but it is some Fp. Yes. And if we want to do the same for generic P, no, better P was for many things, not in this blackboard. Let us change it by alpha. Anyway, so this is a representation of Heisenberg, this is a representation of Heisenberg, and here is the map. And suppose in this case we have vertex operators which are acting from this to this. It means that we have Fi here such that Fi bracket with Hj is alpha Fi plus G. And as I said, such kind of operators are defined by this relation actually uniquely if you choose, like here, that the operator F minus 1 is acting from this to this. Let us do it. Yes, and in this case, my operator F0 is acting from this to this, from this to this, and so on. F0 gives me some map from this space to this. And our question now about the kernel of this. And the statement is that if a vector from here is in a kernel of this operator, then the corresponding, if vector is in the kernel, then the corresponding operator commute with the screening. Again, the the way is following is that if you have some vector, say OZ, and you want to calculate a bracket with the integral of a screening, does not matter what is this. You just have to make a little bit calculation. What does it mean? If you make this calculation, you get as the result some element here. And it has to be 0. And this is not more than that. So, in this case, our problem is that I take such operator, and again, this F0 send vector on the first level to this. Here we have 2 vectors, and it is sending to this. And in the case when alpha is generic, then this map F0 from this to this is surjection. And so the kernel of this, character of this is 1 of Q infinity, character of this is Q times this character of a kernel of this is this. So it is 1 minus Q squared, 1 minus Q cubed, and so on. And this is just the character of vacuum representation of Virasoro. Now, if you are talking about the case if when you have several screenings, then in principle you have to do more or less the same. No, the situation, it is, again, but as a sort of exercise, I can formulate the following. Well, but I said that I'm interested in operators here which are something like HZ or something like that, which commute with F0. But I'm saying that it is also possible to ask which operator commute with something like this. And it is also a reasonable question, and exercise that if you want to do it, you also need to find the kernel of something. Also, you have to produce from this operator acting from this to this, and what you have in the kernel will be things. But if you write like this, it will be combination, but still it is the same problem, more or less the same solution. About this, maybe I will say something a little bit later, but now let us go along the standard way and now, if you are talking about more complicated W-algebra, what you have to do. No, about the case when algebra, maybe not Heisenberg, it is a little bit later, but suppose we have the following situation, that let dimension of H equal, for example, 2. And then about our vertex operators, then I take L1 and L2. And my problem is more or less the same. So I take, now Heisenberg is, dimension of this is 2, I have this, and all is the same, but our indices now are vectors. And L1 and L2 now also vectors in two-dimensional space. But I still have F0, and I want to find, I fix screening from here, and I want to know which operators I commute with both of them. And to determine it, I have prescription at least the same. I have to consider operators from F0 to FL1, and operator from F0 to FL2. And my picture, now I have to organize by the following way. That what is F0 now? This is two-dimensional, so I have HI1 and I have HI2. So I have highest weight vector, then I have H1 minus 1, who is acting 1, H is 1, H minus 1, 2. Then I have something like this, and so on. Then if I want to say the same story, this I have to put on level 1. And it will be FL1, and it has the same structure. 1, then it is H minus 1, H minus 2, and so on. And corresponding vertex operators, from this it is acting to this, it is minus 1 component, and 0 component is acting like this. And we have one more thing. So we have what is like F0, and it is going to FL1 plus FL2. Yes, and so we have rather explicit operators which is acting from this to this. And again, our problem is to determine the kernel of this map. Yes, and no, and in principle, the statement was, if you are doing it by this way, you here, suppose you find some vector here, OZ, suppose, such, or this is in the kernel, and O2Z, it is in the kernel. That they are, no, because they are elements from this, you can consider the operator product of them, and all terms in the operator product also arise from the kernel. Therefore, by this way, you can construct the subspace in the vacuum representation of the Heisenberg algebra in this case, which is closed with respect to operator product. So such kind of construction is always give you the part which is closed with respect to vertex operator product, and so the question which was in this business, which people trying to solve from the very beginnings, 30 or I don't know, 40 years ago when it started, that if you have the collection of vectors, L1, L2, or maybe many of them, and the dimension of space is also big, then when such common kernel of all these operators is non-empty or non-trivial. And no result of such things are let me consider the example which no, it is also old, but not so old as all such things. Suppose we are talking about the following situation. So I want to use fermionic screenings, but this is because kernel of them are bigger. So what does it mean? It means that I can, let me, in this example, dimension of this space is equal 3. And suppose we fix 3 vectors, L1, L2, and L3. And suppose that the scalar product of all of this Li is equal 1. This means the following, that if I take vector L such that LL is equal 1, and if I write down the vertex operator, which is corresponding to this vector, it will be something like this psi. And so vertex operator are corresponding to this vector. So it's vector, suppose it is Lz, it is something Li times E minus I, and this Li are all skew commute. And my problem is now, so if you have such 3 vectors, then the situation now describing by 3 scalar product, L1, L2, L2, L3, L and L1, L3. Yes, some kappa 1, 2, kappa 2, 3, and kappa 1, 3. Yes, and well, so now we have a problem similar to this, but we have more huge Heisenberg and fermions, yes, but between them there are some scalar products like this, and therefore it is the result have to depend on these numbers. So we have some. What is this now? we have F0 again, but now Heisenberg is three-dimensional, and we have F L1 plus F L2 plus F L3. And I can explain what is going on in this case. Suppose that this, and this are generic. So what is going on? Then here, this focus graded space. We have vacuum vector here, then we have something on the first level, something on the second level. On the second level, in a kernel, we have one element. And it will be later some Virasora, and we have some TZ. And if we have Virasora, then operator expansion, this Virasora with itself also belong to our kernel. So it means that in a kernel, we expect to have some space with the character 1, 1 minus q square, 1 minus q cube, and so on. And if these three numbers are generic, then kernel is just this, no more than that. And but algebra become bigger if these three numbers satisfy some condition. And to be honest, the answer, full answer, when kernel actually become bigger, I think it is still now it is not known. But if kappa 1, 2 plus kappa 2, 3 plus kappa 1, 3 is equal minus 1, in this case it is definitely known that the kernel is much bigger. And in this case, the corresponding algebra is really bigger, and actually this is common phenomena what we are talking about, that we have some family of data, and in principle kernel for generic things is rather small, but if data corresponding to something, then kernel become bigger, and in this case, if it is minus 1, then corresponding vertex operator algebra just isomorphic to no, it is UK1 SL2 hat times UK2 SL2 hat times UK3 SL2 hat when K1, K2, K3 is level, K1 plus K2 plus K3 equal minus 4, and we have to make reduction with respect to diagonal. And I do not want to explain precisely what does it mean, but it is some famous and well-known algebra, and this is appear by this way. Yes, and these kappas here, kappa 1, 2, for example, is K3 plus 1. And kappa 2, 3 is K1 plus 1, and so on. And this is the description of this situation. Yes, and but if you are talking about what I started in the beginning, what was quantum KdV, what I said in the very beginning of my lecture. This is the situation where Cartan is one-dimensional. And now but still we can take two vectors, L1 and L2. And we can form the corresponding screening from L1, but these two vectors in this case are just two numbers. And so we can ask no, even here I considered this case, but it was rather special. But nevertheless, it is the case of such kind that I take fermions here and psi from boson fermion corresponding this vector operator corresponding to 1, and psi star is vertex operators corresponding to -1. I can take psi 0 and these two things and just ask what commute with both of them. And in this case, I said that I did not say it, but I can say it, that in this case it is also corresponding, or at least it has some connection with SL2 hat on level 2, -2, and with critical level and so on. And my other example, when I had two components of 1, it means that what? It is L1 equal to L2, but I use different Fourier components, and question is still the same. But what is going on? So if you take just L1 itself, one vertex operator, then my problem was like this. I take this, and operator is acting like this, and I'm interested in kernel of this map. Yes, and suppose, and what if I have some second one, it is also some operator from here which is acting to somewhere. It may be some other space, but structure is the same. And my question is when I can find something non-trivial in the intersection of these two kernels. And surely expectation is in generic situation it is 0. No, top vector surely yes, but no more than that. And this is true. The question where something is interesting is occur if, first of all, L1 plus L2 is 0. And our picture now is looking like this. So here F, 0, here FL, here F minus L, and I have two operators which are acting like this. Yes, and now the question about common kernel, and this common kernel is 0. But if I but I can ask the question a little bit differently. So, well, 0, it means 0, nothing. But in a fork, I can take some vector O and produce operator like this. And the question is it possible that the integral of this, or 0 Fourier component of this, is commute with both of them? And such kind of, no, the answer yes, such kind of object exists, and how to start these things? So, well, I said, and maybe mentioned, that with each some such map with this and with this, one Virasora commute with this because kernel is big and it is something, and other Virasora commute with this. Therefore, we have two Virasoras, and central charge of this Virasora depending only on the length of this vector. So central charge of them will be equal, but they will be different. And so the problem is following. So I have Heisenberg, and I have two embedding of Virasora here. And how much they commute? But first of all, some intersection we definitely have. And it is not easy to see from this my exposition, but in Virasora we have operators L0. And L0 from one Virasora and L0 from other Virasora, they up to some constant are equal. And so it means that these two Virasoras just vector spaces. As vector spaces, if we add constant, they intersect by L0 more or less. So L0 is in the intersection, and the question, do we have something more than that? Yes, and roughly the situation is the following. I want to find operators OZ such that the integrals of OZ commute with this and with this. Yes, and but because this is integral, the expression like this after integration give me 0. Therefore, the following thing is true, that maybe I think I explain a little bit detailed tomorrow, but we have the action of operator something like d over dz here. And this operator is acting like this. So what does it mean? That I said that I have hz, for example, and h prime z. And it is corresponding to some vector, and this is corresponding to to vector where this operator is acting. And if I have h square z, for example, it is corresponding to some vector of level 2. And we have the operator like this, which is first derivative. It is corresponding to some vector of level 3. And this vector is the result of acting of some operator which is acting from the second level to a third. Therefore, if we want to do this, then we have to factorize it f0 by the action of operator d over dz of 0, and we have a map to f1 fl over d over dz of L, and operator f minus L over d over dz of L, and we have to find the kernel of these two. And this is the problem from the linear algebra or usual algebra. What we have to say to solve if we want to find the object which commute with both of them. And let me just explain not this now, but the following. So suppose I have a lattice counterpart of what I said now. Here, the best approximation of what is going on, here it is the following, that we have xi, and xi xg is equal q, xg xi is I less than g, and we have algebra which in principle generalizes xi and xi inverse. This is a0, a, and this is sum of this is summation of ai, and I run from minus infinity to plus infinity. Well, then I have a map. No, my question was following. Screenings maybe S plus is the sum of xi, and S minus is the sum of xi inverse. And we have a maps from a0 to a1, and from a0 to a minus 1, and it is bracket a sent to bracket s plus with a, and here a sent to a bracket s minus with a. And so we have such maps from this to this and to this. And here we have a maps from Fock space to this, from this and to this. And from the first glance, it is looks different, but structure is very, very, very much close. And here we find out the expressions which, no, in principle, Virasora in this language, it is something here which commute with this operator, so which is going to 0 here. And here we just talking about kernel of this map. And if we are considering these more complicated things, that we are talking about the kernel of both of them. But now what is the meaning of this problem d over dz and something like this in this language? But here it was what? We have infinite number of points, infinite suppose, and local expression is something like some function p in xi plus 1, some segment, ai plus s. Yes, and suppose it is by p, let us put, no, it is not power, let us put I here, that p is just some polynomial, but not necessarily polynomial. Generally, it can be more complicated function, but it depends in x. It is local in a sense that it depends on the infinite segment and living somewhere. Yes, and but now let us see that if we are talking about this, then W-algebra in principle, it is such kind of expression which commute with this operator. But if you are talking about integral here, it means that you want to make something integral of this. It means it is summation of pi I. And we are, recall that we are living in zero sector. It means that I want degree of this function or polynomial, does not matter, be 0.
But what is A0?
Now, A0, it is, so here it is something which is degree 0 in x's. So this grading means that degree xi is 0. Degree xy is 1, excuse me. Yes, and it is what I explained yesterday, but in A0 we have typical element xi plus 1 inverse, for example. Yes, and again, so this grading is in corresponding with this grading. So this is more or less like this is more or less like this is more or less like this, and so on. Yes. Anyway, here I'm talking about, I want to ask about such sum when this sum commute with s plus and s minus. And if I want this, what to do? No, because s plus is the sum of xi, and s minus is sum of xi minus 1. They commute with the shift by 1. Therefore, pi I after integration give me something which commute with s if before I need this is 0. Now I need the bracket as be something like full derivative. But it is not derivative. It has to be object which after after integration give us 0. So in this case, we need to form some a minus shift a, like this. If such things is this, then integral of p commute with this plus. And so now problem is following. We want to find out such pi that s plus pi is in full derivative and s minus pi I is also full derivative. Yes, and by the way, in this case, it is possible in lattice case, and in that case also, by the way, it is also possible to present some way to calculate such kind of expressions. Yes, and the fact that such solution of such problem exists actually connected very much with the fact that S plus and S minus in this case, and I said what? That this is a special case actually of the situation which I talked about, because if I take S plus and S minus and consider the algebra which they generate, that this will be nilpotent subalgebra in UQ SL2 hat. Yes, and it is surely it is not a theorem at all, but in some cases, yes, but in all problems of such sort, where we have affine algebra, such kind of problem of finding of solution of similar things can be solved. And here we have kernel, here we have also kernel of like this and so on. And because I have to stop now, and tomorrow I'll explain maybe main technique which are using here when we want to study the situation, why such kind of two maps have common kernel, and what technique can be used for to prove that. Okay.